Alright, so we are talking about holes and slant asymptotes, 6.4, or what am I saying, 2.6 in the book. Um, so in order to graph this, we need to factor the numerator, and we're going to factor that as x plus 2 times x plus 3, and we're going to factor the denominator as x plus 2 times x minus 1. Notice we have an x plus 2 in the numerator and the denominator, so we are getting a whole at x equals negative 2. We have a vertical asymptote at x equals positive 1. We have a 0 at x equals negative 3. And we have a horizontal asymptote at y equals positive 1. So let's put all this together now. First thing I'm going to do is I'm going to sketch in my asymptotes at positive 1 for x and y. So I'm going to sketch that in. I'm going to sketch in my 0 right there. And I know I'm going to have a hole at negative 2, so I need to remember that. But now I can just sketch it in, and I know it's going to look like that over here, because if it were on the other side, I would have a 0, and I don't. And then over here, I know since the multiplicity of my 0 is a odd number, my branch is going opposite sides, so it's going to curve up like that, cross over, and then approach that asymptote of y equals 1, but never cross it. And again, I have a hole right there. So that is my poor imitation of what this function looks like. So now let's take a look at this problem. This is going to be pretty interesting. So first off, recognize that we have a factorable numerator. We can pull out a 3x from each of these, and if I do that, I'm going to be left with an x squared minus a 1 right there. Sorry, I lost my train of thought. And in the denominator, well, my denominator is already factored for me, so I'm going to leave that as it is, but I can factor the numerator further as a difference of 2 squares. So I'm going to have x minus 1 and x plus 1 over x plus 1 squared times x minus 4. Now this is kind of weird. Notice we have an x plus 1 in the numerator, and we have two x plus 1s in the denominator. So even if we took one away and wanted to say there's a hole there, we still have an x plus 1 factor in the denominator, so we're still going to get a vertical asymptote at x equals negative 1. We're going to have another one when x equals positive 4. We're going to have zeros at x equals 0 and x equals positive 1. And if you think about the degree of the function, it's 3x cubed over x cubed. So we're going to have a horizontal asymptote at y equals 3. So let's see if we can piece this together now. Let's draw those asymptotes in first. So horizontal one at 1, 2, 3, going across, and a vertical asymptote at negative 1, and 1, 2, 3, 4, positive 4, and I have zeros. What did I say? At 0, and also at 1. So now let's think about what this function is going to look like. Well, I know that I'm going to be up there, over here, because again, if I was down there, I'd have to cross, and I can't. And same situation over here. And now I need to come up, cross, come back down, and find my asymptote again. So again, this isn't a perfect sketch, but it's going to look something along these lines. This is going to be the general behavior of the graph. And I actually lied to you. I had to redraw that. This graph does actually cross that asymptote ever so briefly there, and then works its way back up to the underside of that horizontal asymptote. So let's look at this problem now. It looks scary, but all we need to do is factor the numerator. And so we're going to get 3x cubed minus 9x squared. If you notice that we have 4 terms here, we are going to use factoring by grouping. So look at the first two terms together, and then look at the last two terms together. What can we factor out of the first two? Well, we can pull out a 3x squared, and you're left behind with an x minus 3. And then if you look at our other term, we can factor out a negative 75, and you're also left with an x minus 3. And that is our goal. We want those to be the same there, because now we can factor that expression as x minus 3 times 3x squared minus 75. Now we can further factor that factor, 3x squared minus 75. We can pull that 3 out and get x minus 3 times x squared minus 25. And holy moly, we can factor some more. 3 times x minus 3 times x plus 5 times x minus 5. So now let's take that and put that whole thing over. X plus 5, notice those are canceling each other out. And we also have x plus 3 quantity squared. So let's think about what we have. Well, in the denominator, I have a VA at x equals negative 3. And note it is multiplicity 2. So it's going to have the tails stay together. We also have zeros at x equals positive 3 and positive 5. And anything else? Well, we have a cubic with a coefficient of 3 over a cubic with a coefficient of 1. So we're going to have a horizontal asymptote at y equals 3. And then finally that whole, we have the whole at x equals negative 5. So now let's just put all of this together, draw in our asymptotes. So 1, 2, 3, got my asymptote there. 0 at x equals 1, 2, 3, and positive 5. And then finally horizontal asymptote at 1, 2, 3. So now let's piece this together. If we look at the left branch, we know we are going to be in the upper branch there, because if I were in the lower branch, I would have to have zeros, and I don't. And we know we also have to start in the upper branch, because that vertical asymptote has a multiplicity of 2. So I'm going to be coming over, and I'm going to come down and cross there, and then I'm going to turn back up as such. So look at my beautiful rendition of this, and then look at the calculator's. Same idea, just your calculator's a little more precise than I am. So now we need to talk about something totally new, but pretty interesting and totally makes sensible, slant asymptotes. So to find a slant asymptote, we're literally going to do some long division here. So we're going to divide x squared minus x minus 2 by our denominator there, our dividend, x minus 1. So x goes into x squared times x times times x is x squared, x times negative 1 is negative x. And so we are subtracting the same expression, so that's going to be 0, and we're going to drop down our negative 2. So pretty quick to see that this is going to be equivalent to x with a remainder of negative 2. And there are a couple ways we can write that. And again, I think it makes sense to look at an example of numbers first. So if you look at, say, 47 divided by 9, well, 47 divided by 9 equals 5 plus 2 ninths. So notice I'm taking my quotient and adding my remainder divided by my divisor. Well, we're going to do the same thing here. We're going to say that this is equivalent to x, which is my quotient, plus my remainder, which in this case is actually minus 2 divided by my divisor, x minus 1. Now this is telling me that if I were to look at really, really big values of x, If you think about this fraction, negative 2 over x minus 1, well, with huge values of x, huge positive or huge negative values, that fraction is essentially equivalent to 0. So, for really big values, our function will approach y equals x. So I still need to look at this, and I can still factor it to get some asymptotes. So if I factor the original numerator, so let's go x minus 2 times x plus 1, and that's over x minus 1. Based off of that, I already know that I'm going to have a vertical asymptote at x equals 1. I know I'm going to have a 0 at x equals 2. And I know I'm going to have another 0 at x equals negative 1. But I also know I'm going to have a slant asymptote at along the line y equals x. So that tells me that this side is going to look like that. And this side is going to look like that. Notice how I'm approaching all of my asymptotes, and that should be like nice and smooth and not lumpy there like mine is. But that's what you should get. It's kind of cool to see how that works. And I'm sorry, I forgot to mention, a slant asymptote is always going to occur when the degree of your numerator is exactly 1 more than the degree of your denominator. You end up with that slant asymptote. Because if you think about it, you're going to end up with a linear term there. So let's look at another one. So again, let's do some long division. We're going to be dividing x plus 1 into x squared minus x. X goes into x squared, x times x is x squared. X times 1 is x, and we are subtracting both of these. So we get negative 2x. And then x goes into negative 2x, negative 2 times. Negative 2 times x is negative 2x. Negative 2 times 1 is negative 2. I'm subtracting that whole thing. So 0 minus negative 2 is actually positive 2. So again, I can rewrite this as x minus 2 plus my remainder 2 divided by my divisor, x plus 1. And again, this is going to go to 0 for really big values of x. So that tells me that my slant asymptote is at x minus 2. But again, let's factor this, and so we can figure out our normal information. So I'm going to factor that as x times x minus 1 and x plus 1 in the denominator. So let's piece it together. I'm going to have a vertical asymptote at negative 1. My slant asymptote, we said, is going to be at x minus 2. So let's sketch that in now. It looks something along those lines. And let's see what else. I have a 0 at x equals 0. And I have a 0 at x equals positive 1. So if you think about this function staying within all of those asymptotes, this guy is going to come down like that and hit those zeros and then curve off that way. And then this fella is going to be stuck down in there. And that should be what it looks like if you graph this on your calculator. Or, roughly. So let's just think about this closure question then real quick. How do you find holes, vertical asymptotes, and horizontal asymptotes? Well, it all comes down to factoring. Factor the numerator, factor your denominator. If you have any identical terms in the numerator and the denominator, you will have a hole. For each additional term in your denominator, you will have a vertical asymptote at each of those solutions, so whenever your denominator is equal to 0. Horizontal asymptote, you got a couple options here. Well, either the degree of your numerator is the same as the degree of your denominator, and then it depends totally on the coefficients, or the degree of your numerator is greater than the degree of your denominator, and you're going to go up to positive or negative infinity, or the degree of your numerator is less than the degree of your denominator, and you're going to have a horizontal asymptote at 0. And then to find the zeros, All you gotta do is factor that numerator, get rid of the wholes, and then whatever's left, whatever makes the numerator 0, will give you your zeros. And then one more question you should be asking yourself, what about slant asymptotes? Well, to get a slant asymptote, take the numerator, long divide it by the denominator, and then you have a slant asymptote at whatever your quotient is. And that should be enough for you to sketch some rational functions.